Efficiency of a kettle experiment.
So what I got here is a kilowatt, which basically what it does is like the power meter you have outside, except this measures it for a plug. What I wanted to do today is to boil some water
And measure the amount of energy used in doing so.
One of the things you do when you teach actually is you learn all sorts of crazy things when you find things out. And so here, this is the base for my kettle. This is the one I have at home. And you can tell it is 1200 watts, so 1.2 kilowatts. So, okay, so that's the output power. So over here, if we look at this kettle, we have 900 milliliters of water in here. I'm going to put a thermometer in here and measure the temperature of the water. So the temperature is 31.4. No, takes time for it to equilibrate. It's 31.5 degrees centigrade. Okay, and I'll just turn this on. So while this is boiling, okay, as you can hear in the background, I would like to actually go ahead and have a look at what the power really is. So I'm going to cycle over, following the directions here, and here it says that the power is 1243 watts. Okay, so it's a little higher than the actual power that was than the power rating that I said earlier. So the water's boiled. It's really hot. It's boiling. I'm going to say that it's 100 degrees centigrade at the end. And as you can see here, I used 0.08 kilowatt hours. The energy input, i.e. the energy that was supplied from the plug through the kilowatt device, was equal to 0.08 kilowatt hours. It's not particularly accurate. I kind of want to just get a ballpark out of it. If you wanted to be more accurate, you probably would want to just heat up the water and more batches of water, so you get and just add up the energies with that device, and it turns out to be about 3 times 10 to the 5 joules. Okay, now the energy output it is equal to mass times the specific heat times the change in temperature. The mass, well, we know it was 900 milliliters, so I can divide that by 1,000. No, take it back. I know that it is about 1.00 grams per milliliter times 4.184 joules per mole per degree Celsius. That's the specific heat of water, and then times the difference in temperature. Now my final temperature was 100 degrees centigrade minus 31.5 degrees centigrade, and that comes out to be about 2.6 times 10 to the 5 joules. Therefore, the efficiency is equal to the useful energy output, which is here, to 2.6 times 10 to the 5, divided by the energy input. Now what I did here, in fact, was that I used a few more digits. You generally don't want to round until the end, so what I used actually here was 2.88 times 10 to the 5 joules, and here I took this number, which is 2.58 times 10 to the 5 joules, and I have to multiply this by 100 to get the number in percentage. I think I got about 90%, which is about as good as I can say it. So where did the rest of that energy go? Well, the kettle has an opening, right? So You lose some heat through that. You also lose some because the kettle's not doesn't have that thick a wall, so you lose some energy through that as well. So 90% efficiency is actually not that bad.